This is Mrs. Appia with Grade 8 Module 3 Similarity, Lesson 4 Fundamental Theory of Similarity. In general, what does the FTS demonstrate or prove? The last few days we have focused on dilation. Now we want to use what we know about dilation to come to some conclusions about the concept of similarity in general. A regular piece of notebook paper can be a great tool for discussing similarity. What do you notice about the lines on the notebook paper? They are parallel. That is to say, they never intersect. Keep that information in mind as we proceed through this activity. On the first line of your paper, mark a point O. We will use this as our center of dilation. Mark a point P a few lines down from center O. And draw a ray OP. Now choose P' farther down the ray, also on the line of the notebook paper. So not in between, but actually on one of the lines. Now use the definition of dilation to describe the lengths along this ray. We know that by dilation, the length of OP' will be equal to the scale factor times the length of OP. Again, the length of the dilated segment will be equal to the scale factor times the length of OP. Now, let's write down the scale factor that we have obtained. So here we know the length of OP is 1, 2, 3 lines. And we're not measuring the length of the segment. What we're doing is we're counting how many lines we have gone down. So we have gone down 1, 2, 3 lines. So the length of OP is 3. And the length of OP' would be 1, 2, 3, 4, 5 segments. So now let's calculate what our scale factor is. Divide by the original length of the segment, and our scale factor is 5/3. And we're just going to leave that as a fraction. Now we're going to draw another ray. Over on this side, let's find point Q. And I'm going to do it on the same line as point P. And we're going to call that Q. Then we're going to draw a ray from O through Q. To dilate point Q. Then, since this is 3 lines down and this is 3 lines down, then our dilated segment here is 5 lines down. Then using the scale factor of 5/3, then Q' would be right here. Next, connect the segment PQ. Next, connect P' to Q'. What do you notice about the lines PQ and PQ'? Notice that the lines fall on the notebook paper. That means that they will be parallel. Next, let's use our protractor to measure OPQ, right here, and OP', Q'. Also, let's write down what we noticed about those lines. We know that PQ is parallel to P', Q'. And next, we're going to measure the angles OPQ and OP', Q'. You can pause the video and connect, or rather measure, your angles. So I've measured my angle and I have 54 degrees. Then I'm going to measure OP', Q'. And again, I have 54 degrees. So what I'm noticing, OP', Q' is 54 degrees, and OP', Q' is 54 degrees. Notice that they're equal in measure. And actually, they must be equal in measure because they are corresponding angles on parallel lines cut by a transversal. Next, let's measure OQP and OQ', P'. Pause the video and measure your angles, and then resume the video. I have 146 degrees for each one of those. And again, they are congruent. So I know that angle OPQ, and I'm going to mark that with one arc, is congruent to the measure of angle OP', Q'. These are corresponding angles on parallel lines, and they are congruent. And then the other pair was the measure of angle OQP, right here, and I'm going to show that with two arcs, and that was congruent to the measure of angle OQ', P'. And I show that with the two arcs, and then this with the one arc. Also, I just wanted to point out to you that in addition to knowing that they are congruent because they are on parallel lines cut by a transversal, that if we took this angle and translated it using the vector P', that would prove, or map one onto the angle onto the other, proving congruence. And we could do the same with these angles on the right side as well. Next, use your centimeter ruler to measure the lengths of segment OP and OP'. And then pause the video and go ahead and measure yours while I measure mine. Alright, so I've got OP measuring 3.4, and I'm using centimeters. Using the centimeter ruler is a good idea because it gives you a more precise and easier to read measure. Also, if your measurements are off by a millimeter or so, that's alright because the difference can be attributed to human error when reading or writing the lines, reading the ruler. Alright, so I had OP, the original segment, 3.4 centimeters. My dilated segment, OP prime, measured 5.6 centimeters. And what we know about dilations is that the length of the dilated segment is equal to the scale factor times the length of the original segment. So my dilated segment was 5.6 and my original segment was 3.4. So if I divide by 3.4 on each side of my equations, that's going to show me what my scale factor is. So I'm going to go ahead and do that division. If I can, never a calculator around when you need it. Alright, that comes to approximately 5.6. And 5.6 is approximately equal to I didn't need that. Alright. Next, let's take a look at the segment on this side. So I'm going to ask you to pause your video and measure your original segment and your dilated segment and calculate your scale factor. Pause the video while you do that, and then I'll write my measurements as well. So I have the measurements OQ is equal to 5 centimeters, and I have OQ prime as equal to 8.5 centimeters. And I want to know, is OQ prime equal to the scale factor times the original segment length? So I have 8.3 is equal to, and our scale factor was 5/3, and I want to know if that is equal to 8.3 is equal to 5/3 times the original length of 5. So I'm going to multiply this, and when I multiply this, it is approximately, not exactly, but approximately equal to. So next, I'd like to measure PQ and P prime Q prime. So I've got PQ, this distance right here, is equal to 6.3 centimeters. And I've got PQ prime equal to 10.4 centimeters. And I want to see what the scale factor is that relates these two segments. I want to know if this segment dilated using the same scale factor as when we dilated these points. So I've got PQ prime is equal to the scale factor times the length of the original segment. And this would be the dilated segment, so they are both primes. So that's P prime, Q prime. And move up a little bit here. And P prime, Q prime was 10.4. And R and the length of PQ, which was 6.3. And I'm going to multiply this times 5/3, which was our scale factor, and see if they are equal. This is 5/3, not 5/13, I just don't have a good eraser. So I have 10.4 on the left, and when I multiply this, it's approximately 10.5, which is very close. And again, you might be off by 1 millimeter because of the just human error. So what this shows is that the third side that's not dilated directly has the same scale factor as the dilated points. Again, we dilated these segments using 5/3, and we dilated this point using 5/3. So you would expect that these have the same scale factor. What we wanted to do when you were measuring these is to find out if this line dilates with the same scale factor of 5/3. If the segment connecting the dilated points dilates with the same scale factor. And the answer is yes, it did. Next, we're going to mark point A on PQ, between P and Q. So pick a point between P and Q and label that A. Then we're going to draw a ray O through A, and then mark A prime on the line as well. O through A, and then we'll call that one A prime. Do you think that the length of OA prime is equal to the scale factor times the length of OA? In other words, does this dilated length have the same scale factor as this dilated length? Let's find out. So go ahead and measure your OA. Measure your OA and OA prime. Boy, I could really use a good ruler or a good eraser right now. I'm just going to start that over. Is OA prime equal to the scale factor times OA? So my segment lengths I have OA as 2.8. Our scale factor is 5/3, and OA prime looks like about 4.6. So I'm going to multiply that and see if that is correct. Will this always happen, no matter what the scale factor or placement of points for Q, A, and B? Well, will this always happen? Will what always happen? Will the corresponding angles be congruent? Will the corresponding sides be proportional? Yes. And I know this, all students doing this exercise have slightly different lengths of segments. And the above statement is true, regardless of the scale factor. Describe the rule or pattern that we have discovered in your own words. I'd like you to pause the video and see if you can, maybe just on a piece of scratch paper, write down the rule or what we have discovered in your own words, and then resume the video and make any corrections that you need to. So the parallel line segments connecting the dilated points have the same scale factor as the dilated points. And here it is with a diagram. The parallel line segments that are connecting the dilated points have the same scale factor as the dilated points. So the relationship between this shorter segment and the longer segment have the same scale factor or are in proportion in the same way that this short segment is comparing to the longer segment. So here is the theorem. Given a dilation with center O and scale factor r, for any 2 points P and Q in the plane so that OP and Q are not collinear, the lines PQ and PQ prime, those are the segments connecting the dilated points, are parallel, and P prime is the dilation of P and Q prime is the dilation of Q. And we also know that this is the dilated segment is equal to the scale factor of the original segment. This segment connects the original points, this segment connects the dilated points, and it will have the same scale factor. So here it is in user-friendly terms. Given a dilation from center O of P and Q, where OP and Q are not collinear, we know that the segment connecting P and Q and the segment connecting P prime Q prime are parallel and have the same scale factor as OP and OP prime and OQ and OQ prime. So we know that the length of the dilated segment is equal to the scale factor times the original segment length. And the length of the other dilated segment is equal to the scale factor times the original. This one should not have a prime after it here. There we go. So this is the length of the original segment times the scale factor equals the length of the dilated point. Then we know that, and these are the segments connecting these points, the length of the original segment times the scale factor will be the length of the dilated segment. So what they're saying is when you use the same scale factor to dilate those points and you connect those points, those two segments have the same scale factor. And that's the fundamental theorem of similarity. Go ahead and copy that and then turn your page. In this diagram, points R and S have been dilated from center O by a scale factor of 3. So OR, scale factor of 3, and you have OR prime. If the length of OR is 2.3 centimeters, what is the length of OR prime? All right, let's use our definition of dilation. We know that the dilated segment, OR prime, is equal to the scale factor times the original length of the segment. And it says to use a scale factor of 3, and it says the original length is 2.3. So we multiply 3 times 2.3 to give us our answer. So the length of OR prime is equal to 6.9 centimeters. Question B. The length of OS is equal to 3.5. What is the length of OS prime? Pause the video and complete that exercise. So we have OS prime is equal to 3 times OS, and that is equal to 3 times 3.5. And so OS prime has a length of 10.5 centimeters. Next, connect point R and point S, and then point R prime to point S prime. And what do you know about those lines RS and RS prime? Pause the video and complete that activity. what I know about those lines is that RS is parallel to R prime S prime. Next, what is the relationship between the length of the original segment RS and the length of the segment R prime S prime? The relationship is that they are proportional. We have R prime S prime is equal to 3 times the length of RS. They are proportional. Question E. Identify pairs of angles that are equal in measure, and how do you know they are equal? So I'm going to go back to that page and look for pairs of angles that are equal in measure. I know that these are parallel lines and that this is a transversal. So one of the things that I know is that corresponding angles are equal in measure. So this one would be angle ORS and OR prime S prime. So we have angle ORS is congruent to angle OR prime S prime. Again, I know that they are corresponding angles on parallel lines cut by a transversal. Also, I could do a translation along R prime of angle R, proving that with transparency paper, mapping this angle onto this angle. So, is there another pair that you see that are equal? Well, how about this angle right here? OSR. What angle is it congruent to? Well, these are parallel lines cut by a transversal. So this angle could map onto this angle along vector S prime, proving congruence. So another pair of angles that we can add to our list here is angle OSR. OSR is congruent to angle OS prime R prime. S prime R prime. Okay, how do I know that they are equal? How do I know that they are equal? They are corresponding angles on parallel lines cut by a transversal. Let's summarize what we have learned in this lesson. If the length of OP prime is equal to a scale factor times the length of OP, and OQ prime is equal to the scale factor times the length of OQ, then the segment connecting the dilated points is equal to the scale factor times the length of the segment connecting the original points. User-friendly terms. Under dilation from center with a scale factor r, a segment multiplied by the scale factor results in the length of the dilated segment. And that's what we did right up here. This is a segment multiplied by the scale factor results in the length of the dilated segment. We also know that the segment connecting the original points is parallel to the segment connecting the dilated points. And that concludes our lesson.